Hello guys, thank you for coming to my channel, and I have been very happy to get some comments on my videos. That most of them are really helpful to me, and today I'm going to demonstrate high resolution STEM imaging, including probe correction. So basically, I will use the probe corrector to tune high order aberrations in STEM mode. So today's objective is to get a really best image in atomic resolution. The sample is the cross gradient gold standard sample, which we usually use for tuning microscope, like for example the distortion correction, yeah, something like that. Um, I try to get the atomic image of that sample. Okay. Um, So here is you are seeing two screens. Actually, I use some tricks. So I actually use a team view to link with my microscope the screen. So basically, we are seeing the TIA here, TM user interface, and I use this one. Actually, my mobile is taking the video in the projection to these two monitor and the panels here. Um, I use a Zoom meeting for this, and actually I'm just recording the screen simultaneously. Um, briefly tell you, so here the left hand the monitor is actually what you are seeing in here, which is TIA, and this in the middle. This monitor is actually the Velox. Is we use this monitor as an imaging, and here is also for imaging for what this one is a Gatan PC. So basically, the digital micrograph is on in this monitor. Um, actually, I try to use this monitor as much as possible because that actually give you more details there and higher resolution. Um, but there is some time I need to use this monitor, so maybe, yeah, I thought that gonna be quite good to see both screens simultaneously. That's why I use these tricks. Um, so little explanation will be helpful for the setup. So what the microscope I'm using is a TMS-JET, and as you see here is a high tension is 300 kV, and yeah, which probe correction and image correction system is installed in the microscope. So today's high resolution TM, I'm gonna use a probe corrector. Um, so I try to mention every single step before I do, so that I want to let you know which kind of step I'm on, so you directly know, okay, what I do or what I'm doing. Also, I really want to take a look at which panels I'm using or which knobs I'm using for the microscope tuning and the imaging. So I think I really hope to give most of information in this video for high resolution TEM. I'm not so sure whether I can give the really 100% the good demonstration today. Probably I could miss something. If that the case happens, I try to prepare another video and insert to this video, so a little bit demonstrate further. I think also it would be nice to prepare a video for um, the probe corrector especially, so where the probe corrector is located in the microscope and what kind of thing the probe corrector is doing for the high order aberration correction. So maybe I'll do that. But today is actually just I go through the daily alignment and then the probe correction. Then I try to get the atomic image that's gonna be the today's objective. Okay. So I load. So the current status is the sample has been inserted. Nothing more than that. So I the load the fact register for the stem. takes a little time, like for example 1 minute. No, okay, it's already done. Okay, because probably I already loaded. Then I open the variable. Then we're gonna see the beam here. Okay, we are on the sample already. So we basically just try to see how the sample look like. Okay. Here probably you're seeing the sample right now, and you're seeing the Runchgram there, and probably I a little bit need to change the gain. These are a little bit saturated. Okay, this location is already good because we have an empty space there, which is for the probe tuning, and also we have the sample there. So I'll bring the eccentric high. So first thing I want to do is I want to bring to the sample to the eccentric high. So basically what we do is actually we are scanning there, and we will get the best contrast we can get in the current cell. That gonna be that actually equivalent to finding eccentric high. So you probably know, I'm not sure whether I need to explain a little bit further. So basically, if we hit the eccentric focus, the probe is focused on the eccentric plane. So it is actually scanning on the eccentric plane. If the sample is out of the eccentric high, then it's kind of like a defocus, right? Because it is focused on the eccentric plane. If we are far away to there, we are actually, our probe sizes get bigger, which is because it can be over focused. Then we want to really bring back to the center, which means actually which is actually equivalent to finding the best contrast. So already nice. A little stigmator but we are not really taking care of the stigmator in the current state. So I bring to the as best as possible. Okay. And actually it is quite good to know the lobe, the eccentric high for specific holder, because most of the case the sample doesn't really, like a sample in the holder doesn't have like a too much difference in the sample by sample, but the holder by holder there is a specific range for the eccentric high. So it is quite good to memorize the range for the eccentric high, which is again the holder specific information. So this holder is actually like near to align our microscope. Okay, I will bring the probe in the center, and we are seeing like monochromator. So probably it would be better to a little bit go through our microscope and a little bit explain the probe correction. So as I told you, we are in the 3 kV high tension, and here is we are using the monochromator for tuning the gun lens. So basically we use monochromator focus and shift to change the current on the sample. So we need to actually center monochromator a little bit later. And so here condenser aperture I'm using 70, and our like convergence angle, corresponding convergence angle is a 30 millirad. And here is our camera length is 91 millimeter, which is actually appropriate condition for the STEM imaging. So I'm not going to change those things. So first thing I want to do is actually I want to the center monochromator. And the point, today's point, it's actually we have a probe corrector above the sample. And here's one thing. We do not want to change the microscope above the probe corrector much because we already set the optimal condition to be corrected by the probe corrector. I mean, we set the microscope to be corrected by the probe corrector. So we do not want to change the microscope. So most of the thing, if it is possible, we want to just change the probe corrector rather than changing microscope. So we only want to use the microscope for fine tuning at the end. So I go through like the steps. First of all, I'm gonna center the monochromator. You already see some shadow from the monochromator. So in that case, actually we can just active here the monochromator tune, the focus and the shift. Actually intensity knob here is now is a focusing, defocusing of the monochromator. It's actually equivalent to be changed the gun lens. And probably I will go to the probe mode. I think it will be much easier. Okay, our beam is, our probe is there, and our, you see here the screen current, our focus monochromator as small as possible, and using multifunction AY, I'm gonna center it a little bit, focus further. Focus further to center like as best. Now we are nearly seeing the whole monochromator. Then I will get, so now screen current is very, very high. So I want to reduce this for appropriate condition for the STEM imaging. Actually, we can go down to the 50 picoamp. Actually, this can be differ with, depend on the sample or whatever you want to do. You need to know the like appropriate condition for your STEM imaging. So even this 50 picoamp can be also too high current for some samples. So in that case, you probably want to reduce further. But today, our sample is actually stable, which is gold sample again. We really do not need to reduce much. And just I want to get a good condition for the probe correction. Okay, so you are already centered, and so again we are not using the like a microscope, the beam shift, because as I told you, we do not want to really change the microscope. In that case, I'm gonna change by the probe corrector to move the beam. So we are not changing the microscope itself, we are changing the probe corrector. Again, this is actually good, actually important point. Okay, I bring to its center, and first thing I want to do, the next thing I want to do is actually I want to center C2. For C2 we can a little bit modify our probe. Okay, so I go to tune. So I'm gonna center, but actually one can use such panel, but I'm actually, personally, I really like to tune manually. So we are wobbling intensity now to see where is a center, but it's more or less correct already. Little bit off, very little bit, but I do not really want to change much because now it's already good. Yeah. So actually also here is a condensed center of the probe, which means actually we are changing the C3, C2 simultaneously, and we correct. But this is more or less perfect right now. And rotation center in the beam tilt, we can actually, yeah, it's a little bit off. So like a rotation center, so I'm gonna tilt the beam using probe corrector, not the knob in the not changing the microscope. Okay. Okay, now it's already really good. Okay, more is perfect. Okay, done. And and I will make the probe as small as possible. But you see there is a stigmator. Probably we'll see a bad image. Okay, so our sample is there. So we can tune. I want to tune by, actually we can tune the microscope like two ways. One is actually you just see the image and you tune the like a A1, A2, B2. But another way is actually we just try to look at the launch gram. For the probe correction, automatically we need to get certain good level for good status for the imaging. That is actually the first thing we need to do. So here I think we can find the better eccentric high. And if you see here, if you see the launch gram, okay, very strong A1. So we can tune the using probe corrector locally. You already get our two big step. Yeah. I think B2 is nearly perfect. Let's see the image. It's get much better, right? And now actually we can use the probe corrector. Basically, actually, depending on sample and depending on the microscope, maybe the appropriate magnification for the probe correcting can be different. But that should really based on your experience. But I think this is gonna be really good for already good condition for the probe tuning. So I'm gonna tune the probe. Hi, I prepared another video to explain a little bit more in details of probe corrector. So here is basically, yeah, I'm compare with the TM and STEM. Actually, if you are looking for a video for probe correction and high resolution STEM, actually those kind of description is actually you likely familiar with already. But just case some of beginners are watching my video, so I started from the scratch. Actually, basically we are doing STEM imaging
today. And here is actually difference between the TM and the STEM. So in case of the illumination is we are focused in moving, right? Our probe is scanning on the sample. So the magnification actually solely depend on the scan area, and the resolution is actually depends on the probe site. Because this is very important. So the most important aspect in the STEM imaging is to focus the probe as small as possible. But the problem is, as you know, the lens is not always perfect. The lens has intrinsic imperfection, and which cause the aberrations. So using to imagine just we are using one lens to focus the coming electron beam on the sample, but the outside can be focused more than we wanted, and inside is when the inside the beam actually just in focus, then actually as a result we're gonna have a very big the probe, which directly result in the hampered the resolution in the STEM imaging. So actually basically we want to correct such a thing in the probe corrector. So again, we want to correct the spatial aberration of the lens by the corrector. So actually I do not really describe everything in details because I don't think it is a really good idea to make this video very long. So just basically I will tell you the idea only. So the probe correction system actually located in the between the condenser lens system and the object lens. So here, so we use like a dodeca the pores of corrector. So we are compensating the lens aberration by the the probe corrector showing here. So actually the geometry of the probe corrector can be depends on system by system. So here is it can be octapore, so also quadrapore, and basically when the beam is coming with some aberration, we are measuring the shape of the beam, and we are compensating the beam shape to be round and small as possible with double correction system. Okay, this is very simple. So if there is a strong A1, then you probably see here is some elongation in certain axis. Actually, this is just basically astigmatism. And if we tune the A1 correctly, then we're gonna have a little bit better, like elongation can be reduced. And if we have A2 resulting in like a not circular magnification in the lunchgram. If there is a B2, changing the focus to the under focus, the strongest area of the magnification is actually flipped over left to right, to up to the down, vice versa. And not only low order aberration, actually we also have very high order aberration. Here is the attributal symmetry, and here is a radial order. We have like a CS spatial aberration, and A3 and S3, so on. So we want to correct such thing to get our probe as perfect as possible. This is actually what we are doing with probe correction. So again, we are measuring the shape of the probe, and if the shape of the probe is not ideal, which means it's not circular and which cannot be small, then we are compensating the shape by the probe correction system. Okay?
So I'm going to open the probe corrector. Yep. Here is I'm gonna use just try to tune the low order like aberrations like a C1, A1, A2, B2, and here is WD is rotation center. So basically what the microscope right now doing is actually changing the focus, under focus or over focus, and try to get the probe image. Okay, so this is and after we calculate the probe, the image, I mean the shape of the probe, then we can calculate back to the C1, A2, A1, A2, B2, and the rotation center based on their. This one is based on their the tilting angle. So we can correct here 0 to seconds, all of them. So we just take a look at the numbers there. So if you see the color, the deepness of the color is actually telling you what is a current the problem. If it's more yellow, it's more problematic, and it is more white, then it is actually no problem at all. So now actually you see here A2 has a problem. So we are changing by the A2 by 75% of this value. So which means we are actually not 100% of trust in this calculation. So we are a little bit reduce the correction values so that actually we can move within within a little bit not as big as the number here. So our probe is already looks very good, round and small. So one more 0 second. Actually here we actually do not need to put too long time here because once we will change the high order aberration in the tabular measurement, the lower order aberration will be changed as well. So actually, so that's gonna be, I will say, enough. And I will stop here and we can update the probe. So so our probe size is several angstrom right now, but we're gonna improve further. And then we go to tabular measurement. So I'm firstly go to the fast measurement. Fast measurements means we are not measuring too much. So basically here what we are doing is we are tilting our probe, and as the same way we calculate the shape of our probe. Based on that, we are calculating the aberrations. Maybe now is actually measuring the standard way. There are many tabulars right now. Basically, actually, we can start in the standard, but it just takes longer time than the fast is. So here now we see what is the problem actually. So I'm gonna correct up to the third over aberration to the S3, but it's already good. So now is that only we have a trouble in the lower aberration. Then we just accept and 0 to second and go to the tabular measurement. But actually, yeah, for demonstration purpose, actually, it would be good. The previous tuning is really bad. Then I can use a probe corrector step by step. But for current condition is really good, so there is nothing much I can do. So A2 has a problem right now, so we correct A2. Still has a problem. I think today's video can be very, very short, shorter than I expected. So after probe correction, we'll get several images of the sample. That's all actually. But actually, I think it is quite good to have some troubles, so that once we met some troubles, we can actually try to fix it. During that process, we really learn a lot. But today is too smooth. So A2 once more. Since the high order aberration is nearly perfect, actually in the real experiments, I'd rather start directly to the sample with this the condition. So for example, if we stop and we update, so our probe is already less than 1 angstrom. And if we exclude low order aberration, then our probe is nearly 70 picometer. Okay, this is already really good. So just for demonstration purpose, I just try one more, the standard measurement. If it still gives us a good probe, maybe then I will just go to the imaging. Normally for the high resolution imaging, we actually do not really need such a too sharp probe. Actually, even if the probe is angstrom size, yeah, it's no problem to get the atomic image. So now A2 has a problem in D4. Maybe, yeah, just for today, we just tune up to D4 because my video is ending too fast. So I'm gonna tune the D4 up to D4. So here then I will tune the D4 75% and I go to the gain to the low order aberration correction. Actually, it is also very informative to see the lunchgram during the measurement, whether how it looks like. But I think it's very good enough actually. With this automatic measuring system is actually very easy. Nothing really micropist need to do. Just look at the number. If number is exceeding the confidence value, then we are tuning. This is just we just do iteratively, and if your like interest of the probe condition reached, then we just stop it and we go to the imaging. That's actually all. Okay, I think this is already good to get a. Oh, a little bit, that's good. Maybe we still have low order aberration. Also, we have B2. You see some asymmetry of the probe. Okay, one more tableau measurement. Actually, you probably see here the sample is contaminated in the center. So where our probe is, so in this case, actually, this is actually harmful for the best tuning. So in this case, we need to a little bit move the stage to the new area. That will help for the better tuning. Or before the measurement, we can simply do the beam shower. Like a 2 minute or 3 minutes of beam shower really help avoid the contamination. So I think it's get worse. So which actually I believe because the sample position, I move a little bit, and I'm gonna change F3 and C3. Then I go to the lower the aberration correction. C3, S3, and lower the aberration correction. Yeah. Yeah, I moved to the new area. Our contaminated area is there. That will really affect our measurement. A2, B2. Yeah, our probe is already really nice. 76 picometer. Even we exclude lower the aberration, we are nearly go to the optimum condition. So last tabular measurement, and I go to the imaging. I'm quite sure even if we stop here, we're gonna see a very nice atomic image in the gold sample. But the gold nanoparticles, our sample is actually gold nanoparticles. So we just probably see many the lattices because we are not in the we do not have specific zone axis of the sample. The probe is already looks very nice. So we have A3 and A2. Yeah, maybe this. Yeah, that's gonna be the really last measurement. Yeah, I think that's gonna be enough for today's purpose, and maybe we'll see a much better image already. And seeing the launch gram, I'm gonna focus the probe. I feel we have a B2 right now. You see there is a B2. Maybe I need to correct a little bit more. again. Yeah, I still see some B2 in the probe. So I already tuned a little bit further. The focus is not correct exactly. Now actually high order aberration is okay. So actually we do not really need to go to the high order aberration. High order aberration is rather stable than low order aberration. So basically, if you want to get the best high resolution image by STEM mode, so many people will recommend to use the standard sample to correct high order aberration, then just to change the sample and then just correct the low order aberration. That will really help you a lot, especially for measuring unknown sample, because high order aberration will be stable after you change the order, but the low order aberration can be a little bit affected by the sample changing. Also, if your sample is magnetic sample, then will affect the objective lens. Then the low order aberration can be tuned, can be changed a little bit. Okay, I think it will be okay. I think this is gonna be okay for today. Okay. Yeah. Let's see lunch RAM. Yeah. Good. So maybe we go to somewhere. Yeah. Yeah. We already tuned the probe nicely, so I use the Velux in this monitor. We zoom in a little bit. Yeah, there is a quite good area. Good. Maybe here is a zone X. We are in the zone X axis here. Not 100%ly, but still good. We are seeing already the atomic images. So maybe we take an image, but temper is dripped too much. Yeah, it's not good. Maybe a little bit bigger. Yeah. So if I change contrast a little bit, you see here is atomic images here. It's already very good. It's actually very high resolution right now. We are seeing like all the atomic lattices, and even here is probably the zone axis here. We see very good atomic image. Actually, this is for today. Here is now our probe is a little bit defocused. So in the lunchroom, actually, we are infinitely magnifying atoms there. So we basically looking at the lunchroom, so we can tune our probe quite nicely already. So maybe last image. This gonna be all for today. So actually I wanted to cover how to use probe corrector to correct our probe, especially for high order aberration. Okay. Okay, thank you for joining. Actually, I always want to make a not very long video because the watching like more than 1 hour the tutorial video is actually somehow it is kind of boring. So I really hope this video will help you, and this video is quite efficient to learn in your side. And if you have a question, yeah, please comment or send me an email.